Throughout its long history, our Earth has proven time and again that the cosmos can be home to worlds drastically different from what we know. Beyond the familiar boundaries of the solar system lie the so-called exoplanets, celestial bodies orbiting stars other than our Sun, often at inconceivable distances. Merely half a century ago, the very existence of these distant planets was mostly theoretical. Now, thanks to modern technology, astronomers discover hundreds of new ones each year. Many of these newly found worlds are hot Jupiters, orbiting so close to their stars that they reach searing temperatures. Others may be cold, icy orbs drifting in the darkness of their outer systems, forever locked in frigid isolation. Then we have the truly exotic cases with extreme temperature swings, toxic atmospheres, or even surfaces made of unusual materials. Today we will focus on one of the most remarkable examples from this cosmic abundance, a planet known as 55 Cancri e, located in the star system 55 Cancri. This so-called diamond planet in super-Earth stands out for its intense conditions and for fueling bold hypotheses about the interplay of fiery geology and high-temperature chemistry. It is difficult to find a more striking illustration of how far a planet's environment may deviate from the familiar Earth-like image. Although 55 Cancri e orbits so close to its star that its surface might literally be melting, hints of volcanic or magmatic activity combined with the possibility of a carbon-rich interior to spark constant scientific intrigue. In this discussion, we will shed light on the captivating world of 55 Cancri e, part of the famed 55 Cancri system, and see just how bizarre planetary conditions can become once we move beyond the bounds of the solar system. More than half a century ago, star 55 Cancri, cataloged also as Roan Cancri, had already been relatively well studied, being only about 41 light-years away, which is close by cosmic standards. Yet the presence of planets orbiting this star wasn't conclusively proven until the 1990s, when astronomers systematically searched for exoplanets using Doppler spectroscopy, detecting minuscule variations in a star's radial velocity caused by the gravitational pull of orbiting planets. The first planets in the 55 Cancri system were identified in the late 1990s. Not long afterward, researchers realized that the system might contain at least 4 or 5 significant objects. Ultimately, around 2004, evidence pointed to the existence of the super-Earth designated 55 Cancri e, and that discovery became one of the key findings that demonstrated just how unusual short-period planets close to their stars could be. This object quickly rose to fame when some astronomers proposed the possibility of a diamond-rich interior. The interest only grew as subsequent refinements were made to its orbital parameters and physical properties. Scientists observed the planet's transits, which helped refine estimates of its radius and mass. Each new measurement spurred fresh speculations about its internal structure. Combined with the fact that 55 Cancri is relatively easy to view from Earth, in the northern constellation of Cancer, these discoveries turned 55 Cancri e into a prime target for exoplanetary study campaigns. By current estimates, 55 Cancri e is classified as a super-Earth. Its radius is roughly twice that of Earth, around 1.9 to 2.0 Earth radii, while its mass appears to be about 7 to 8 times Earth's. Such values yield a considerable overall density and led to the hypothesis that the planet might be extremely rich in carbon, potentially containing so much carbon that it could harbor enormous quantities of diamond in its depths. This striking idea captured public and scientific attention alike, since previously the concept of a diamond-laden planet seemed the stuff of science fiction. The story gained further momentum when calculations suggested that if the planet's mass is about 8 times Earth's, while its radius is only about twice Earth's, its density far exceeds Earth's, but remains somewhat below that of pure iron or other heavier elements. By comparison, our Earth's radius is about 6,370 kilometers, whereas 55 Cancri e's could be approximately 12,000 kilometers. Meanwhile, having 7 to 8 times Earth's mass would result in a gravitational force likely 2 or 3 times stronger than Earth's. A human visitor, if one could exist there at all, would thus experience crushing gravity. Yet even that would be overshadowed by the unimaginable heat that scorches the planet's surface. Scientists propose that 55 Cancri E orbits extremely close to its star, which itself is a bit smaller and cooler than our Sun, but still emits enough radiation to fry any nearby object. The planet's orbital period of around 18 hours, some studies say about 17, but either way extremely short, results in searing exposure to its star's energy. As a result, surface temperatures are thought to soar to between 2,700 and 3,000 Kelvin, above 2,400 degrees Celsius. Under these conditions, nearly all silicate rocks and metals would melt, forming magma oceans and even vaporizing minerals. Some astronomers propose that carbon might form extensive diamond regions in the planet's mantle, although this remains very speculative. Another possibility is that 55 Cancri E is more or less Earth-like in its composition, simply packed with heavier elements, with an iron core and a silicate mantle that is superheated near the surface. Either way, given the extreme heat, the planet's outer layers may not have anything resembling stable terrain. Instead, there could be a roiling expanse of molten rock, turning 55 Cancri A into what some call a lava planet. The earliest detections of planets in the 55 Cancri system relied on measuring the star's radial velocity variations. Observers at facilities including Lick Observatory and the Keck Observatory eventually confirmed the presence of multiple large bodies around 55 Cancri. However, the super-Earth 55 Cancri E remained elusive until improved instrumentation raised our capacity to detect modest-sized planets close to their stars. When the planet was identified around 2004, it drew attention as one of the tightest orbiting super-Earths known at that time. Observations with the Spitzer Space Telescope in the infrared allowed scientists to witness the planet's transit and refine its radius. Not long afterwards, speculation about a diamond planet captured the imagination, though direct evidence for such diamond-laden layers remains absent. Nonetheless, the prospect of unusual carbon-based chemistry spurred interest well beyond the scientific community. Telescopes such as Hubble made attempts to glean further data, particularly concerning any atmosphere the planet might hold, by searching for spectral signatures during transits. Results have been mixed, leaving the question open as to whether 55 Cancri E retains any gases at all at such punishing temperatures. Recent research with the James Webb Space Telescope holds the promise of clarifying the composition of its upper layers, assuming they exist. Talking about surface features on 55 Cancri E must be done carefully, given the inferno on its day side that can exceed 2,000 degrees Celsius. Most materials would liquefy at such temperatures, creating magma seas, heavy element vapors, and clouds of silicate dust swirling in the heat. Some astronomers suggest that one side of the planet faces the star more or less consistently, typical of tidal locking, but radial velocity data and other measurements imply that 55 Cancri E might instead occupy a more intricate spin-orbit resonance, perhaps rotating in a way that regularly exposes different regions to the star's intense energy. As a result, planetary days or nights might spawn cataclysmic volcanic events whenever lava breaks through and vents are created. The daytime hemisphere, inundated with stellar radiation, could generate mineral evaporation, while the cooler hemisphere re-solidifies these vapors or channels them underground. Some models even discuss the possibility of stone rain, in which silicate droplets condense out of superheated clouds. Though these concepts might seem far-fetched, certain theoretical studies suggest that, at extreme temperatures and pressures, planetary surfaces can behave in ways wholly alien to the volcanism we see on Earth. A crucial debate involves whether or not 55 Cancri E has an atmosphere. Logically, with a surface that hot, one would expect any lightweight gas envelope to have been stripped away by the star's radiation. Yet the planet's estimated mass, on the order of 8 Earth masses, indicates a gravity that may retain heavier elements. Some scientists propose that 55 Cancri E might have an atmosphere composed of silicate vapors, metal oxides, or other heavy species, rather than the hydrogen-helium envelopes typical of gas giants. The star 55 Cancri bombards this world with potent stellar winds, so any original atmosphere likely evaporated eons ago. Meanwhile, if the planet has an internal mechanism that outgasses minerals or volatiles, that might partially replenish or cycle certain gases. Additionally, the possibility of heat redistribution from day to night side, if the planet's interior is geologically active, has led to a variety of climate or weather models, each pointing to a truly infernal system of heat transfer. In essence, conditions on 55 Cancri E would be so harsh and dynamic that they redefine our usual concepts of weather, leaving us to imagine a place of molten flows and ephemeral clouds of vaporized rock. The uniqueness of 55 Cancri E is owed to several factors. First, it orbits extremely close to its star, yet remains only about twice Earth's radius. That alone indicates a highly compressed, ultra-hot environment, unlike anything in our solar system. Second, its potentially carbon-rich composition stirs speculation that enormous diamond deposits might form under intense pressure, an idea that is scientifically plausible under certain circumstances, even if not firmly proven here. Third, the planet resides in a multi-planet system, giving astronomers a chance to observe complex gravitational interplay among multiple planets. Fourth, 55 Cancri itself is near enough to Earth for repeated and detailed observations, allowing for much finer data on transits and radial velocities than many other exoplanets. Finally, the interplay of tidal forces, possible spin-orbit resonance, and unstoppable surface heat might produce a type of extreme tectonics, if any plates or layers do exist in a semi-solid state. The planet thus serves as a fascinating natural laboratory for exploring how super-Earths might be formed, migrate, and evolve close to their parent stars. There are, of course, no immediate plans to send spacecraft to a star system over 40 light-years away. This is far beyond any near-future capability. Nevertheless, astronomers rely on an array of telescopes, both ground-based and in space, to gather every possible clue. The Hubble Space Telescope has attempted observations in the ultraviolet, while Spitzer and Chandra have taken readings in the infrared and X-ray ranges, respectively, aiming to discern something about the interplay between the planet and its star. But the James Webb Space Telescope represents a new level of infrared sensitivity, possibly enabling the detection of extremely fine spectral features related to the planetary atmosphere, or exosphere, if it exists. By analyzing starlight passing through any gaseous layer, JWST might pick up signs of sodium, silicon oxides, or carbon-based molecules in minute concentrations, an outcome that would yield a direct glimpse into 55 Cancri-E's scorching environment. In the future, improved instruments, some with mirrors over 30 meters in diameter, may similarly refine their detection capabilities. Yet for now, we remain reliant on spectroscopic hints rather than direct close-up exploration. In conclusion, 55 Cancri E offers a vivid reminder that not all planets mirror the baseline we know as Earth. A short orbital period of just 18 hours, a surface temperature presumably hot enough to melt or even vaporize rock, and the suggestion of unusual carbon chemistry stand out as features that would be impossible in our own solar system. Observing this planet gives astronomers crucial insights into the ways planetary systems form and evolve, as well as broadening our grasp of the chemical, geological, and atmospheric processes that can take place across the cosmos. If such a hellish world can remain stable in close proximity to its star, then perhaps countless other systems in our galaxy present even more outlandish conditions. Already, astronomers discuss planets with glass rains, pitch-black gas giants that absorb nearly all incoming light, and cold super-Neptunes that revolve in the dim outskirts of their stars. Yet 55 Cancri still commands special attention. The stark contrasts in its environment, coupled with the notion of diamond layers and the powerful star-planet interactions at play, keep it in the spotlight for observational campaigns. With each fresh look at its transit, each new measurement of radial velocity, we refine our understanding of this extreme super-Earth and maybe the physics behind planets that push the limits of what we once considered feasible. Ultimately, 55 Cancri E underscores how the universe goes far beyond our ready-made categories, creating astonishing configurations of matter, energy, and forces. Who can predict what even more bizarre objects await detection? Every new piece of data about 55 Cancri E might inspire us to explore possible parallels in other star systems, including those that might have kinder environments reminiscent of Earth. But for now, 55 Cancri E stands as a striking testament to cosmic diversity, a crucible of molten stone and possibly exotic geology, provoking us to question just how singular Earth's own path might be. If you find yourself curious about such extreme planets, or have theories as to how a world can survive with such colossal heat and possible diamond caverns, feel free to share your thoughts. Public and scientific enthusiasm for these tormented realms continues to grow, meaning we can look forward to more refined spectroscopic data, surprising results, and perhaps brand new revelations about how planets form and whether life itself could emerge under truly exotic conditions. Let us stay in touch with all the wonders the universe has to offer and anticipate eagerly the next wave of cosmic surprises that is sure to come.